of a wall we have considered, and to understand this geometry, we are considering that we are standing in front of a thickness of that particular wall. Okay, we are standing in front of a thickness of that particular wall. So only the wall thickness and the wall height is visible. So in one dimensional, we have to take that much only. Okay, and we have considered that the one surface of a wall is maintained at a T1 degree Celsius temperature, whereas other surface is maintained at a T2 degree Celsius. So here the T1 is greater than T2. Okay, T1 is greater than T2. So in the diagram we have shown it on the basis of a height from the base. Okay, so T1 is greater than T2, so that heat will be transferred from this surface, left hand surface, to the right hand surface. Okay, and that amount of heat transfer is Q amount of heat transfer. Okay, so total amount of heat is transfer is equal to Q. Okay, and the wall material is homogeneous material, and the material thermal conductivity is uniform throughout the material or throughout the wall, and it is equal to K. Okay, and we have drawn the circuit diagram or electrical analogy diagram for this particular wall. Okay, so current is analogous to heat transfer. So current is flowing in the electrical circuit. Here the heat is flowing in a thermal circuit. Current is flowing due to the potential difference. Here the heat is flowing due to the temperature difference. And whereas the resistance uh, uh, opposes to the heat, resistance in electrical circuit, resistance opposes to the flow of the current in a same manner. In a thermal circuit, the thermal resistance will be opposes to the flow of the heat. Okay, to the flow of the heat. Okay, and that resistance we have calculated by using the Ohms, by using the Fourier's law. Okay, and it is equal to L divided by K multiplied by A, where L is the thickness of wall, K is the thermal conductivity of a wall material, and A is the perpendicular area for the flow of heat, perpendicular area for the flow of the heat. Okay, now further we have derived that equation on the basis of a general heat conduction equation in a Cartesian coordinate system. So why we are using the Cartesian coordinate system for the wall? Because wall is one kind of a rectangular geometry. Okay, and every point on the wall or the rectangular geometry can be measured or can be pointed out by using x y z direction. Okay, or x y z coordinate system. So for that reason we are using the general heat conduction equation for Cartesian in Cartesian coordinate system for the wall. Okay, and we have discussed this equation: del square T plus Q suffix G multiplied by 1 upon K, or Q suffix G divided by K is equal to 1 upon alpha multiplied by dabba T divided by dabba small t. So it is equation number 1. Now here we have applied some assumption. Assumption number 1 is there is no internal heat generation. That is nothing but wall is not generating any kind of a heat. Okay, then the heat conduction is a steady state, and the heat flow is a unidirectional, or it is flowing only in a x direction. These are the assumption, and after applying this assumption on this equation, we will get the equation as the del square T is equal to 0. In that, del square is the vector operator for x, y, z direction. That it suggests that the temperature is changing with respect to x, y, z direction. So here only we are going to consider that heat is flowing only in the x direction. So that we have to consider that the heat flowing in a y direction, or temperature changing with respect to y direction and temperature changing with respect to z direction equal to 0. So that our derivation will be deduced into dabba 2t divided by dabba x square is equal to 0. So that will be the equation number 2. And further, our consideration is that up till now, until now, we have discussed the general heat conduction equation in a Cartesian coordinate system for the small element. So in that case, it is required to apply the partial differentiation equation. Okay, And when we are considering the whole geometry or the large body, so in that case we have to consider the complete derivative. In that case we have to consider the complete derivative. So it will be converted, this equation dabba 2t divided by dabba x square will be converted into d2t divided by dx square is equal to 0. Now we have to convert in the form of a complete equation. We have to find out uh, 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 mm, we have to find out the temperature change with respect to distance, or we can say that we have to find out the temperature profile, okay, or temperature distribution. So in that case we need to integrate this equation, okay. We have to remove out the derivatives, and to remove the derivatives we have to integrate that equation. So integration of d2t divided by dx square, okay. So in first integration, first derivative will be cancelled, and one constant after integration, it is a mathematical law that when you are integrating an equation you have to add up one constant, okay. So after integration we will get dt divided by dx is equal to c1. C1 is one constant. Then we have split up this uh, dividation, dt divided by dx, and we have transferred dx on that side, and dt we have kept on the left side only. So dt is equal to c1 multiplied by dx, which will be useful to integrate once again, okay, which will be useful to integrate once again. So once again we have integrated that. Then the integration of dt will be equal to t only. Integration of dx, c1 is the constant. Then integration of dx is x only. So c1 multiplied by x. And once again we have integrating this equation, so that we have to add up one more constant that is equal to c2. Okay. Then there are boundary conditions. Okay. What are the condition at the boundary of that particular body? That is nothing but the boundary condition of particular object, okay. So when x is equal to 0, okay, so boundary condition means what? When we started measuring, so we have to start from the 0, okay, we have to start from the 0. If you considering that we are measuring the length from this distance, okay, from this particular point, so at this particular point the x is equal to 0 we need to consider, okay. And the complete length is 10 centimeter, then 10 centimeter we have to consider it at this particular point. So x is equal to 0 will be the boundary condition, and the property at this particular boundary condition we have to consider. So when x is equal to 0, t equal to t1 is the first boundary condition, and the second boundary condition is when x is equal to l at this particular point. When x is equal to l at that point, t becomes t2. T becomes t2. That is the simple boundary condition, okay. And that boundary condition we have considered over here. That boundary condition we have considered over here, that is when x is equal to 0, t becomes t1, and when x is equal to l, t becomes t2. Now this boundary condition we have to apply for the equation number 3 to carry out the equations for c1 and c2, or to carry out the values for c1 and c2, okay. So the apply first boundary condition, t is equal to c1 multiplied by x plus c2 is our equation number 3. In that we have to put up the values of first boundary condition. When x is equal to 0, t becomes t1, okay. So we will get t1 is equal to c2, okay, we will get t1 is equal to c2. Then apply second, when x is equal to l at that point, t becomes t2. So t2 is equal to c1 multiplied by l plus c2, okay, where we know the value of a c2. So just put up the value of a c2 as t1 in this equation. So we will get t2 is equal to c1 multiplied by l plus t1. And if you rearrange this equation in the format of a c1, so we will get the value for, or the equation for c1 as c1 is equal to t2 minus t1 divided by l, okay. Now we carried out both the values of c1 and c2, or both the equations for c1 and c2. Just put up that two values in the equation number 3, okay. So put values of c1 and c2 in equation number 3. We will get the equation as t is equal to t2 minus t1 divided by l multiplied by x plus t1, okay. So t2 minus t1 divided by l is the value of c1, and t1 is the value for the c2, okay. So these two constants we have carried out. Then if you compare this equation with the line equation, okay, if you compare this equation with the line equation, so line equation, we know that y is equal to mx plus c, okay, straight line equation, y is equal to mx plus c. So same format, this equation is there. So that is nothing but we can consider t, x and c, okay. So y is equal to mx plus c. So y we can correlate with the t, x as it is, m we can correlate with t2 minus t1 divided by l, and c we can compare with the t1. So we can say that this temperature distribution in a wall is in a straight line, or we can say that the temperature distribution in wall is a linear temperature distribution. What it signifies, linear temperature distribution, that it will signify that the temperature change, or the change in temperature with respect to a distance, on a on graph, will provide you a straight line, okay. On a graph, it will provide you a straight line, okay. And there is no any thermal conductivity present over here. There is no thermal conductivity symbol present in this particular equation. So we can say that the temperature distribution is independent of a thermal conductivity, okay. Further, we have deduced that equation to remember, or to recall it easily. We have converted this equation in the form of a t minus t1 divided by t2 minus t1 is equal to x divided by l, okay. So which is the temperature distribution equation, okay. Whether you understood everything about this derivation, now we have to find out the heat transfer, okay, total heat transfer. So we know the Fourier's law. For in a wall, heat is transferred because of a conduction only, conduction mode of a heat transfer, okay. There is no fluid present in the wall, so there will not be a convection, okay, and there will not be a radiation, okay. So that we can say that the heat transfer in a wall is a conduction heat transfer, and for the conduction heat transfer, we need to apply the Fourier's law. Fourier's law, we know that Q is equal to minus K multiplied by A multiplied by dt divided by dx, okay. So K and A are the constant terminologies. The change is only in temperature and the distance, okay. Change is only in the temperature and the distance, that is dx, or the thickness, okay. So our equation number 4, just we have discussed this equation, t is equal to t2 minus t1 divided by l multiplied by x plus t1. This is our equation number 4. This equation, once again, we have to consider over here. T is equal to t2 minus t1 divided by l multiplied by x plus t1. And to find out the dt divided by dx value, we have to differentiate this equation. We have to differentiate this equation with respect to x. We have to differentiate this equation with respect to x. So differentiate with respect to x. So differentiation of t is the variable, okay, whereas t2, t1, l, t1 are the constant, okay. So t is the variable. So differentiation of a t will be dt divided by dx, okay. Then here, this is the constant, t2 is the constant, t1 is the constant, okay, l is the constant. So that we can say that this constant will not be differentiated, only variable is x. So differentiation with respect to x of x will be equal to 1, okay. And differentiation of t1, so t1 is once again a constant, so differentiation of a t1 only will become a 0. So we will get the differentiation of equation number 4 is equal to dt divided by dx is equal to t2 minus t1 divided by l, okay. T2 minus t1 divided by l. So just put up the value of dt divided by dx in equation, in Fourier's equation. So we will get the equation as q is equal to minus k multiplied by a multiplied by t2 minus t1 divided by l, okay. T2 minus t1 divided by l, okay. So now next we have to absorb this negative sign inside the bracket, okay. We have to absorb this negative sign inside the bracket. So after absorbing negative sign inside the bracket, it will be t2 becomes minus t2 and minus t1 become plus t1, okay. Minus t1 become plus t1. So our equation will become q is equal to k multiplied by a multiplied by t1 minus t2 divided by l. Q is equal to k multiplied by a multiplied by into bracket t1 minus t2 divided by l. So what is changed? Just we have absorbed this negative sign inside the bracket. Okay, and T1 becomes minus T1 becomes plus T1, and plus T2 becomes minus T2. So we have just rearranged the bracket quantities as T1 minus T2. Okay. So further, if you want to find out the thermal resistance, so we have to rearrange the equation without changing its significance. Okay. So just we have transfer the Q numerator Q multiplied by A in the denominator side. So equation will becomes Q is equal to T1 minus T2 whole divided by L divided by K multiplied by A. Okay. And we know that L divided by K multiplied by A is the thermal resistance. Q L divided by K multiplied by A is the thermal resistance for the conduction. So we can say that Q is equal to T1 minus T2 whole divided by thermal resistance for the conduction. RTH in bracket RTH bracket complete suffix conduction. Okay. Whether you understood how to determine the equation for wall for the heat transfer. Okay. So write down heat transfer in continue with the previous derivation. Heat transfer in a plane wall. Okay, heat transfer in a plane wall from Fourier's law. From Fourier's law. From Fourier's law. From Fourier's law. Q is equal to minus K multiplied by A minus K multiplied by A multiplied by dt divided by dx multiplied by dt divided by dx minus K multiplied by A multiplied by dt divided by dx next from equation 4 from equation 4 from equation 4 equation 4 is T is equal to equation 4 is T is equal to in bracket T2 minus T1 T2 minus T1 divided by L bracket complete multiply by x multiply by x multiply by x plus T1 plus T1 plus T1. Okay, now we have to differentiate this equation to find out the equation for dt divided by dx. Okay, differentiate with respect to x, differentiate with respect to x, differentiate with respect to x, differentiate with respect to x. After differentiation we will get dt divided by dx, dt divided by dx, or differentiation of a t with respect to x, differentiation of t with respect to x is equal to t2 minus t1 t2 minus t1 t2 minus t1 whole divided by L, T2 minus T1 divided by L. So we have determined dt by dx. Just put up this dt divided by dx in equation number 5 or our Fourier's equation. So equation 5 becomes Q is equal to minus K multiply by A multiply by A multiply by A multiply by T2 minus T1 T2 minus T1 T2 minus T1 whole divided by L, T2 minus T1 whole divided by L. Okay, in next step we have to absorb this outside negative sign inside the bracket. Okay, so Q is equal to K multiply by A K multiplied by A multiplied by T1 minus T2 multiplied by T1 minus T2 T1 minus T2 divided by L divided by L divided by L. Okay. Next, we have to rearrange this equation without changing its significance. Okay, without changing its significance. So just we have to transfer K multiplied by A to the denominator side without changing its significance. Okay. So we will get the equation as Q is equal to T1 minus T2 whole divided by T1 minus T2 whole divided by L divided by K multiplied by A. L divided by K multiplied by A. Okay. Further, we know that L divided by K multiplied by is the resistance offered by the wall for the heat transfer for conduction. So therefore, Q is equal to T1 minus T2 divided by RTH conduction. Okay. So thermal resistance for conduction heat transfer. RTH in bracket RTH bracket complete suffix conduction. So RTH means thermal resistance and conduction shows that it is the resistance for the conduction heat transfer. Okay. RTH conduction. Okay. Now this is about the A part, that is heat transfer or heat conduction through plane wall. Okay, heat conduction through plane wall. Now the second part of this particular point is heat transfer through composite wall. Heat transfer through composite wall. Composite wall means what? First, we should know that what is meant by plane wall. Plane wall is having only one material. Okay, plane wall is having only one material. Okay, and it is manufactured by using one kind of a material. And composite wall is nothing but it is having different kinds of a material. Okay, so or the layers of a material. Okay, now where these composite walls are used, that is more important, and why the composite walls are used, it is also important. So first thing is nothing but we have to discuss the application of this composite wall. Okay, so application of this composite wall, if we know that cold storages. Okay, first one is cold storage. Second one, we can say that the furnaces. Okay, in the industries, furnaces are used. And third thing is nothing but petrochemical tanks, where these composite walls are used. Okay, where these composite walls are used. So now, why these composite walls are used? Okay, I have told you some applications of a composite walls. Now, why these composite walls are used for cold storages, for petrochemical tanks, for furnaces? Okay, so in cold storage, what is required? It is requirement of the cold storage that less amount of heat should be entered inside the chamber. Okay, less amount of heat should be entered inside the chamber. Okay, so for that reason, more insulation should be provided. Okay, more insulation should be provided to the compartment wall. Okay, so we can say that this is the base wall, and A is the base wall, B is the first insulation provided on the base wall, and C is the second insulation provided on the base wall. Okay, so here in cold storages, requirement is that the less amount of heat should be entered in a compartment or in the chamber. Okay, so that the efficiency of that cold storage will get increased. Okay, so requirement of cold storage that the temperature of that particular chamber should be lower as possible as required. Okay, so and it will be maintained by using the refrigeration and air conditioning system. Okay, now if the more heat will be entered in the cold storage, then it will impact on the efficiency of refrigeration and air conditioning system. It will impact on the efficiency of refrigeration and air conditioning system. How it will it impact? Because the more load will be implemented on the system. Okay, so more work should be done by the air conditioning system. Okay, and due to that, the more electric energy will be consumed, and so that the efficiency of cold storages will be lesser if you are not using the composite walls, or if you are not using the insulations. Okay, so now in case of furnaces, similar kind of application. Furnace is a similar kind of application. In case of a furnaces also, what is the requirement? The less amount of heat should be released from that particular furnace to the outside environment. Okay, so more amount of heat should be present in the furnace only. Okay, more amount of heat should be present in the furnace only, so that the efficiency of furnace will get increased. So to avoid this heat transfer from inside a surface of a furnace to outside environment, we need to provide the insulation to the base material of a furnace, to the base material of a furnace. So if you say that this is the A material is the base material of a furnace, then we have provided the insulation on that particular base material. As a B material, we can say that as the insulation, and C material as a second insulation on the second insulation on the base material. Okay, now and in a similar fashion, in a petrochemical tanks also, if the more heat will be entered in a petrochemical tanks, then we know that the vaporization temperature of petrochemicals like petrol, diesel is very low. Okay, vaporization temperature, that is nothing but at what temperature it will get vaporized. Okay, that is the vaporization temperature. It will convert it into liquid to the vapor, that is nothing but vaporization temperature. Now petrochemicals having very less uh, vaporization temperature, near about 30 to 40 degrees Celsius, or less than that. Okay, less than that. So if heat will be entered in the tank, the more petrol will get vaporized. Okay, heat will entered in the tank, then more petrol will get vaporized. So that reason, to reduce this particular loss, we have to avoid the heat to enter in that particular tank, so that we have to provide the insulation. We have to provide the insulation to such a tanks. So here we have to consider that A is the best material, B is the first insulation provided over that, and C is the second insulation provided over that. Okay. Now this is the general importance of composite wall. Okay. Now we have considered this diagram. Okay. Let us consider that. Uh, Let us consider that the A wall surface is maintained at a T1 degree Celsius temperature, which is higher than the other temperatures. Okay, here we are going to consider that T1 is greater than T2, T2 is greater than T3, and T3 is greater than T4. Okay, so T1 and T4 are the surface temperatures. Okay, T1 and T4 are the surface temperature which are exposed to the environment. Okay, so let us say T1 is the internal wall temperature of a furnace. Okay, and T4 is the external wall temperature of a furnace. Okay, whereas T2 and T3 are the interface temperatures. Okay, between two walls, what that where the walls are connected, that is nothing but we are saying that interface is happening between two walls, and temperature between these two walls we have to consider as a T2, and similar fashion interface between interface कैसे? हो? हो. हो. सकाळी सकाळी बरं. So, sorry for the interruption. So interface between A and B wall, we have to consider that where these two walls are connected, that is nothing but the interface between two walls. And at that interface, what is the temperature? T2 is the temperature between this interface between two walls, A and B. In a similar fashion, the interface between B and C, where these two walls are connected to each other. So at that particular point, what is the temperature? So that temperature equal to T3. Okay. So T1 and T4 are the surface temperatures, and T2 and T3 are the interface temperature. So here the temperature profile is also shown. Okay. Temperature profile is also shown. Now you are saying that whether it is straight line, as we have discussed that in a plane wall. So the temperature profile is linear for the plane wall. Okay, it is not linear for the composite wall, because in a plane wall the thermal conductivity is constant. Okay, in a plane wall, or this wall is made up of one material, so that the thermal conductivity of this wall, particular a wall, is constant as a k suffix a. We have to consider it as a k suffix a, so that the thermal conductivity is constant for this particular wall. So we will get the linear temperature profile, straight line, for the plane wall or one single wall. Okay, whereas if you consider the composite wall, it will not be same, because the thermal conductivities of a different material will be differ. Okay, will be differ. So in composite wall it will not be a straight line, but in a single wall, in that composite wall, for a single wall, the temperature profile will be linear. Okay, temperature profile will be linear. Getting everyone? Now here, for the derivation purpose, we are going to consider that the T1 and T4 are the outside surface temperature. Okay, and T1 is greater than T2, T2 is greater than T3, and T3 is greater than T4, so that the heat is flowing from this particular surface to this particular surface. Okay, heat is flowing from this particular surface, left side surface, to the right side surface. Okay, and the thermal conductivity of wall A, B, C as K suffix A, K suffix B, and K suffix C. Okay, K suffix A is the thermal conductivity of wall A. Wall, if you want to say it as a wall, or if you want to say it as a slab. Okay, you can say it as a slab also, you can say it as a wall also. Once again, we have to consider it as a one directional heat flow, so that we have considered only one dimensional geometry of a composite wall, only one dimensional geometry of a composite wall, by considering we are standing in front of a thickness of that particular wall, so that we will get the thickness of the slab A as L suffix A, thickness of slab B as L suffix B, and thickness of slab C as L suffix C. Okay, these are the thicknesses of a slab, respective slabs. Okay, so now here we have to consider that the heat flow throughout the slab is constant. Okay, heat flow throughout the slab is constant. What it means? Heat flow throughout the slab is constant. What it means? So heat flow through the slab A or wall A is Q. Okay, is Q. The similar amount of heat is flowing through slab B is equal to Q, and similar amount of heat is flowing through slab C, that is also a Q. Okay, so total heat flowing through the composite slab is constant. Okay, total heat flowing through composite slab is constant, and it is equal to Q. It is equal to Q. Important point. If you want to note down, please note down that point. Now, if you apply the electrical analogy for this particular composite slab, then it will be looks like in this manner. Okay, so Q amount of heat is flowing through the circuit, thermal circuit, and initial temperature, this surface temperature is T1. This wall A thermal resistance will be RTH suffix A. Then second temperature T2. Okay, then second wall thermal resistance RTHB, then third temperature T3, and then third resistance for wall C is R suffix C, RTH suffix C, and the last fourth temperature will be T4. So the circuit, thermal circuit diagram will be in this manner. Okay, getting everyone? Whether you understood the diagram? Okay, is there any question, any doubt? Now further, let's consider, we are starting the derivation related to the composites law. So here we are going to consider that L suffix A, L suffix B, L suffix C equal to thickness of slabs or the walls A, B, C respectively. Okay, thicknesses of slabs A, B, C respectively. Then next, thermal conductivities K suffix A, K suffix B and K suffix C is equal to thermal conductivities of materials A, B, C respectively. Okay, so A wall is having different material, B wall is having different material, and C wall is having different material. So different thermal conductivities we will get for the different material. So K suffix A, K suffix B and K suffix C are the thermal conductivity or conductivities of materials A, B, C respectively. Then we have discussed that T1 and T4 are the surface temperatures. Okay, so exterior temperature, exterior wall temperatures are nothing but T1 and T4, which will be considered as the surface temperature, and the T2 and T3 are the interface temperatures. Okay, T2 and T3 are interface temperature. Now further, as we have discussed, since the quantity of heat transfer per unit time through each slab is same, okay, we have discussed that the heat transfer through slab A is equal to the heat transfer through slab B and is equal to heat transfer through slab C is equal to total heat transfer. Okay, what it means, the quantity of heat transmitted per unit time through each slab is same. It means that the total amount of heat transfer through all the slab is equal to the heat transfer through each slab. Okay, total amount of heat transfer through all the slab is equal to heat transfer through each individual slab. Means what? Here we are saying that total amount of heat transfer is Q. Okay, total amount of heat transfer is Q. Okay, so similar heat will be transferred, similar amount of heat transfer should happen through slab A, similar amount of heat transfers will happen through slab B, and similar amount of heat will transfer through slab C. Okay, getting everyone? Is there any doubt, any question? Whether you understood or not, please let me know. What is meant by composite wall and this particular diagram, and how the heat is constant throughout the slab and for each individual slab. Is there any doubt, any question? Whether you understood, please let me know, because I'm getting confused that whether you are understanding this particular concept or not. Okay, great. Okay, shall I move ahead? Okay, so we have discussed that T1, T3, T4 are the surface temperature and T2, T3 are the interface temperature. Since the quantity of heat transmitted per unit time through each slab is same, okay, so we can consider the Fourier's law. Once again, conduction, for the conduction only one law is important, that is Fourier's law. So on that basis we have to derive the equations. Okay, so from Fourier's law we know that we have a Fourier's law, and it suggests that Q is equal to minus K multiplied by A multiplied by dt divided by dx. Okay, Q is equal to minus K multiplied by A multiplied by dt divided by dx. Now if you apply this particular Fourier's law for the slab A, okay, for the slab A. Now remember also here is only another important point, that in a composite slab, okay, so its heights are equal, okay, heights are equal, and its lengths are equal, okay, lengths are equal, so that we can say that the area for each slab is constant one. Area is not going to change. Okay, heat is transforming in this direction, and area perpendicular to this particular slab will be constant for each slab. मैं क्या बोल रहा हूं, आप समझ रहे हैं क्या? जो एरिया ए स्लैब का होगा जो परपेंडिकुलर टू हीट फ्लो होगा, वही एरिया बी स्लैब का होगा परपेंडिकुलर टू हीट फ्लो होगा, और वही एरिया स्लैब सी का होगा. ओके, बिकॉज द थिकनेसेस आर गोइंग टू वैरी. हम कभी ऐसा नहीं करते कि एक कंप्लीट वॉल 10 सेंटीमीटर की है तो आधे स्लैब पे डिफरेंट कलर देंगे और आधे स्लैब पे डिफरेंट कलर देंगे, और आधे वॉल पे डिफरेंट कलर देंगे और आधे वॉल पे डिफरेंट कलर देंगे. नहीं तो ऐसा कभी नहीं करते कि आधे वॉल पे ही कलर देंगे और आधी वॉल बिना कलर की छोड़ देंगे. सो कलर मीन्स व्हाट? वन काइंड ऑफ अ लेयर. ओके, सो दैट विल बी अ कंपोजिट स्लैब आल्सो. That will be the composite wall if you are coloring the wall, because we are adding one more thickness over this the base wall by doing the painting or by coloring that particular wall. So similar fashion, you'll never add the half color, or you'll never do the half coloring of a wall. So if you want to do it, you have to perform the coloring, or you have to perform the insulation over the complete wall. Okay, so the area perpendicular to the heat flow will be same for the A, B, and C, and which is equal to capital A, which is equal to capital A. Okay, so here in equation, in Fourier's equation also, we have to consider it as a constant, as capital A, and for slab A, B, and C. Okay, for slab A, B, and C. So for slab A, if you apply the Fourier's law, slab A is nothing but what? This is the first slab. Now for slab A, the initial temperature is T1 and final temperature is T2. Okay, for slab A, initial temperature is T1 and from final temperature is T2, and heat is flowing from this surface to this surface. Okay, and its thickness is equal to L suffix A, and its thermal conductivity is K suffix A. Its thermal conductivity is K suffix A, and its thickness is L suffix A. So heat transfer through slab A will be equal to, okay, heat transfer through slab A will be equal to, for slab A, so amount of heat transfer will be equal to Q, and it is equal to K suffix A, which is the thermal conductivity of slab A, multiplied by area, which is that particular area, the area which is perpendicular to heat flow. So area multiplied by T1 minus T2 divided by L suffix A. So T1 minus T2, T1 is the initial temperature, and T2 is the next temperature. Here negative sign we have not provided because this negative sign is absorbed inside the bracket, as we have discussed earlier. This negative sign is absorbed inside the bracket, so that T2 minus T1 will become T1 minus T2. Okay, and whole divided by thickness of that particular slab, thickness of slab A. Okay, so K suffix A multiplied by T1 minus T2 divided by L suffix A. Okay, so that will be the equation for heat flow through slab A. Heat flow through slab A. Now we have to rearrange that equation in the form of a temperature difference. Rearranging above equation will provide you. So we have to rearrange this equation in the form of a temperature difference. So temperature difference T1 minus T2. Okay, T1 minus T2. Here we have just shifted remaining part to the left side. Okay, remaining part, but we have keeping only T1 minus T2 on the right side, and other quantities we have shifted to the left side. So what it will becomes? It will becomes T1 minus T2 equal to Q multiplied by L suffix A whole divided by K suffix A multiplied by A, where this Q is the heat transfer, L suffix A is the thickness of slab A, K suffix A is the thermal conductivity of slab A, and capital A is the area which is perpendicular to heat flow. Area which is perpendicular to heat flow. Getting everyone? So that will be our equation number 1. Okay, after rearranging the Fourier's equation for slab A, we have provided it as a equation number 1. Okay, similar fashion we are going to perform for a slab B also. Okay, slab B, for slab B, once again we will check the diagram. For slab B, initial temperature is T2. Okay, for slab B, initial temperature is T2, and the second wall temperature or second surface temperature is T3. Okay, so and its thermal conductivity is K suffix B. Okay, and its thickness is L suffix B. Okay, its thickness is L suffix B. Okay, so on that basis, on that data, we can apply the Fourier's law for the slab B. We can apply the Fourier's law for slab B. So similarly, for slab B, Q is equal to heat transfer through slab B equal to K suffix B multiplied by area multiplied by T2 minus T3 divided by L suffix B. Okay, and once again we have to rearrange this equation in the form of a temperature difference. Okay, so just we have transfer remaining quantities towards the left side, and we have converted this equation in the form of a temperature difference. So we will get the equation as T2 minus T3 is equal to Q multiplied by L suffix B divided by K suffix B multiplied by A. Okay, T2 minus T3 is equal to Q multiplied by L suffix B whole divided by K suffix B multiplied by A. So this is equation number 2. This is equation number 2. In a similar fashion, we have applied the Fourier's equation for slab C. Now for slab C, what are the extreme point temperature? Slab C is this one, and its thermal conductivity is K suffix C. Okay, and its thickness is L suffix C, and the initial temperature for slab C is T3, and the final temperature for slab C is T4. Okay, so by considering this given data or the diagram data, we have to apply the Fourier's law to slab C. Okay, we have to apply the Fourier's law to slab C. Okay, so we have applied this Fourier's law to slab C. So we will get the equation for the heat transfer through slab C, that is heat transfer through slab C, it is equal to Q equal to K suffix C multiplied by area multiplied by T3 minus T4 whole divided by L suffix B whole divided by L suffix C. Here I have to write L suffix C. Okay, L suffix C. Okay, okay. So further we have rearranged that equation in the form of a temperature difference. So we will get the equation as T3 minus T4 equal to Q multiplied by L suffix C whole divided by K suffix C multiplied by A. Okay, now we get the three equation in the form of a temperature difference. We'll get the equation. Okay, three equations. One, we'll get the equation in the form of a temperature. We'll get the equation in the form of a temperature differences. Okay, now we have to add this all three equation. Okay, we have to add this all three equation. So equation number 1, 2, 3, we have to add up addition in a such a manner that left side addition should be done on a left side only, and right side addition should be done on the right side only. Okay, left side addition, that is the temperature difference addition, should be done on the left side only, and the right side quantity addition should be done on the right side only. Okay, so equation from the equation number 1, the temperature difference is T1 minus T2, and from equation number 2, the temperature differences are T2 minus T3, and from the equation number 3, temperature differences are T3 minus T4. We have added all these three temperature differences and equal to, from equation number 1, Q multiplied by L suffix A divided by K suffix A multiplied by A, plus from equation number 2, Q multiplied by L suffix B divided by K suffix B multiplied by A, and from equation 3, plus Q multiplied by L suffix C divided by K suffix C multiplied by A. Okay, now here minus T2 plus T2 will be cancelled, minus T3 plus T3 will be cancelled. Okay, and from the left side only remaining part is plus T1 and minus T4. Okay, from the left side what is remaining? Plus T1 and minus T4. Okay, so at the left side remaining part is T1 minus T4 only. Okay, T1 minus T4 only. From the right side, the Q is the constant, and it is present in all three terms. Okay, it is present in all three terms, so that we have taken it outside the bracket, or we have taken it as a common. Okay, so we will get the equation as T1 minus T4 equal to Q into bracket L suffix A whole divided by L suffix A divided by K suffix A multiplied by A, plus L suffix B divided by K suffix B multiplied by A, plus L suffix C divided by K suffix C multiplied by A. Now next we have to convert this equation in the form of a heat transfer, so that this particular bracket will be transferred towards the left side. Okay, we have to convert this equation in the form of a heat transfer, so that this particular bracket we have to transfer to the left side. So the equation will becomes q is equal to t1 minus t4 whole divided by this particular bracket, okay, getting everyone? Now further we know that L suffix A divided by K suffix A multiplied by A is the thermal resistance offered by slab A, whereas L suffix B divided by K suffix B multiplied by A is the thermal resistance offered by the slab B, and L suffix C divided by K suffix C multiplied by A is the thermal resistance offered by the slab C for the heat transfer. So that the, as we know that L RTH A is equal to L suffix A multiplied by K suffix A multiplied by area, and RTH B is equal to L suffix B divided by K suffix B multiplied by area, and R suffix C is equal to L suffix C divided by K suffix C multiplied by area. So that we can write, therefore Q is equal to T1 minus T4 whole divided by addition or summation of all the thermal resistance. Okay, summation of all the thermal resistance. So that is nothing but T1 minus T4 divided by thermal resistance offered by slab A plus thermal resistance offered by slab B and thermal resistance offered by slab C. So this is the equation for 3 slabs. Okay, this is the equation for heat transfer through 3 slabs. Now if you consider that there are n number of slabs, okay, if there are n number of slabs, we can modify this equation as, okay, there are 3 slabs, so that the temperature difference is T1 minus T4. If there are 5 slabs, then the temperature difference will be T1 minus T6. Okay, if there are 10 slabs, then the temperature difference will be T1 minus T11. Okay, so if there are n slabs, then the temperature difference will be T1 minus T suffix n plus 1. Okay, T suffix n plus 1. Okay, and on the denominator side, we have to add up all the thermal resistance offered by the slab. So the summation from 1 to n of thermal resistance. Okay, so thermal resistance means what? L divided by K multiplied by A for the particular slab. Addition of L divided by K multiplied A for the all the slabs. Okay, for all the slabs or particular slabs. Okay, so that will be the composite slab derivation. This will be the composite slab or composite wall derivation. Getting everyone? Whether you understood? So write up part we will do in the next lecture. Okay, so whether you understood or no or not, please let me know in the chat box. Okay, whether you are getting or not. Is there any doubt, any question? Is there any doubt? Please let me know in the chat box. Okay, great. Others also please reply. Important derivation, and there is more weightage for this particular composite slab and the plain wall or the composite wall in GATE examination. Okay, in GATE examination, these formulas are very much important in the sense of your GATE examination. Okay, so near about 8 to 10 marks question for this particular subject, and the fixed question on the composite wall. One fixed question, 2-mark question will be there in the GATE examination on this particular composite slab. If anybody attended the GATE examination, then that particular person will understood how much it is important. Okay, so if you know the formulas, you will get easily 2 marks. Okay, you will get easily 2 marks. Okay, in GATE examination, and we know that how much it is important for our regular examination also. Okay, so we'll discuss a write-up part in the next lecture, and also the problems on this particular plain wall and the composite wall in the next lecture. Okay, so today, I think 1 to 2 p.m. there is a plastic engineering lecture that I'm going to take over that particular lecture, and in that lecture we'll discuss all the things. So tab tak ke liye thank you, and just put up your roll numbers in the chat box, and you can join More sir lecture. जास्तच उतावळ झालेत lecture घ्यायला. Okay, I think the test is there, so for that purpose, he is excited. Remaining student, please leave this meeting. Just put up your roll numbers and you can leave this particular meeting and join another lecture.